Imagine a world where machines don't just follow instructions. They understand context, anticipate needs, and even reason through problems like a human. This isn't science fiction. It's the reality of modern large language models, and at the heart of their intelligence lies a deceptively simple yet profoundly powerful mechanism: attention. But attention isn't magic. It's a mathematical engine that allows models to weigh the importance of different parts of input data: words, phrases, even entire sentences, depending on the task at hand. And while the original Transformer architecture introduced this concept in 2017, the real breakthrough came not from inventing attention, but from refining it. Let's dive into the technical heart of how attention works, and why recent advances like mixture of experts and FlashAttention are pushing the boundaries of what's possible. At its core, attention computes a weighted sum of values, where the weights are determined by how relevant each input is to the current query. Think of it like reading a paragraph. When you're trying to answer a specific question, your eyes don't scan every word equally. You focus on certain phrases, skip others, and mentally link related ideas. That's exactly what attention does, but in a differentiable, mathematically precise way. The key formula is the scaled dot product attention. Attention Q, K, V equals softmax. Q letter 1D40 / square root DK, V. Q stands for query, the current focus of the model. K is the key, what the model compares against. V is the value, the actual content to be retrieved. The dot product between Q and K measures similarity. But why divide by square root DK? Because as the dimensionality of the keys increases, the dot products grow large, making the softmax output too sharp, almost binary. Scaling keeps the gradient stable and prevents the model from over-concentrating on a single input. Now here's where it gets interesting. The original attention mechanism is quadratic in time and memory complexity. For a sequence of length n, you compute n2 attention scores. That means processing a 10,000-word document. That's 100 million operations just for attention. For long documents or real-time applications, this becomes a bottleneck. Enter FlashAttention, a revolutionary optimization that rewrites the way attention is computed. Instead of materializing the full attention matrix in memory, FlashAttention breaks the computation into smaller, tiled blocks that fit into GPU memory. It uses a recursive formula to compute the softmax without storing the entire matrix, reducing memory usage by up to 50% and speeding up training by 2-3x. But there's more. FlashAttention isn't just faster, it's more numerically stable. By avoiding intermediate overflow and using a clever algorithmic trick called fused softmax, it maintains precision even with very large inputs. And then there's the mixture of experts, another paradigm shift. Instead of every token passing through the same set of parameters, MoE allows the model to dynamically route input to only a subset of experts, specialized subnetworks within the model. Imagine a library where each book is an expert. When you ask a question about quantum physics, only the physics experts are consulted. The rest remain silent. That's how MoE works. Each token in the input sequence activates only a few of the experts, typically 2 per token, based on a learned routing mechanism. This means the model can have hundreds or even thousands of experts, but only a fraction are active at any time. The result? Massive parameter counts, think 100 billion or more, but effective compute that stays low. MoE also introduces a load balancing loss during training to ensure no single expert gets overused. Otherwise, the model risks becoming unbalanced, with some experts doing all the work while others sit idle. But the real power of MoE emerges when combined with attention. In models like Mixtral or Google's LLM, attention is applied within each expert, and the outputs are then combined. This creates a hierarchical intelligence. Experts specialize in different aspects of language, and attention helps them focus on the most relevant parts of the input before making their contribution. Now consider the implications. With FlashAttention reducing memory overhead and MoE enabling massive scale without proportional compute cost, we're no longer limited by the size of the model. We're limited only by our ability to train it efficiently. And that's where the future lies, not in bigger models for the sake of size, but in smarter architectures that scale intelligently. We're moving beyond brute force parameter growth. We're building systems that learn to learn, systems that can reason, adapt, and generalize with fewer resources. So the next time you ask a question to an AI, remember, behind that simple response lies a symphony of attention, routing, and optimization, engineered not just to respond, but to understand. This is the real frontier of AI, not just what models can do, but how they do it. And the best part? We're just getting started.